Hello and welcome to this video on linear modeling. Many relationships can be modeled in a linear way. So for example, if I buy B cans of baked beans, it costs B times the cost of one can of baked beans. And we could write the formula C equals KB, where C is the total cost, K is the price of one can, B is the number of cans of baked beans. This relationship is going to be a proportional relationship since it's a straight line passing through the origin, because 0 cans of baked beans doesn't cost anything. Alternatively, a taxi fare might have the form C equals KD plus S, where C again is the cost, in this case of the taxi, K is the price per mile, D is the distance in miles, and S is the standard fare you get charged before you go anywhere. This relationship is still linear, it's a straight line, but it's not proportional since there's no origin. There's a standard fare added, so 0 miles is not 0 pence. In this section, our linear models will be of the second non-proportional type. In this video, we're going to be looking at two examples, one about giraffes and one about the 100 meters world record. So here's the first one about giraffes. The height, h meters of a giraffe, t years after birth, is modeled by a linear equation, h equals mt plus c. Exactly 1 year after the giraffe was born, its height was 3.0 meters, and exactly 4 years after it was born, its height was 5.4 meters. So our questions: use the data to find the values of m and c in the linear model, hence state the equation of the linear model relating h and t. Use the model to find the height of a giraffe, which is exactly 3 years old. What does the model suggest? That the giraffe's height was at birth. Exactly 6 years after birth, the height of a giraffe is measured as 6.84 meters. Comment on whether or not the measurement supports the idea of the linear model, and then finally state a limitation of our model. So in part A, where we're asked to find the values of m and c, we're going to use simultaneous equations. So we can substitute a height of 3.0 with t equals 1, and we can substitute h equals 5.4 when t is 4, giving us the equations 3.0 equals 1m plus c and 5.4 equals 4m plus c. They've both got a plus c, so we can simply subtract them. That gives us that 3m is 2.4 and hence m is 0.8. So our model is h equals 0.8c plus c because m is 0.8. And then we can substitute the height again of say 3.0 and the m as 1, sorry, c as 1. And that gives us c as 2.2. So substituting those into our formula gives us the answer to b, which is that h equals 0.8t plus 2.2. So now we have our model of h equals 0.8t plus 2.2, we can start using it. So in part C, we need to use the model to find the height when it's exactly 3 years old, which means that t is 3. So we can simply substitute t equals 3 into our equation, giving us an answer of 4.6 meters. And don't forget the units. In part D, what does it suggest it was at birth? Well, that's when t is 0. So again, we just substitute 0 into there. Obviously 0 times 0.8 is 0, so it's just the c value, the 2.2 meters, which is our answer. For E, we're told that the height is 6.84 meters after 6 years. So if you substitute 6 into the formula, we get an answer of 7.0. And if we're asked to compare that with the actual measurement of 6.84, we could work out, say, the percentage difference between them. And it's fairly close. It's a good model. There's only a sort of 2-point-something% difference between them. And then finally, F, a limitation. Well, of course, this model, it's a linear model. Lines don't stop. So in theory, this model predicts that when the giraffe is infinitely old and the height is infinite, and similarly, when it's 50 years old, it's probably going to be taller than would be sensible. So the limitation of the model is that it's probably only going to work over a certain number of years. And now we're going to look at our second example about the 100-meter world record. So in 1960, the world record was 10.0 seconds, set by the German Armin Harry. And in 2009, the men's 100-meter world record was 9.58 seconds, as it still is, set by the Jamaican Usain Bolt. And it suggested that a model is devised to predict the world record r seconds, t years after the first recorded world record was set in 1912. Again, we're asked for a linear model. Okay, and we're going to use it to make a prediction. We're going to state a limitation of it, and we're going to comment on it based on actual data. So just like in the giraffe example, we're given two sets of information. We're given a particular amount at a certain time and another amount at a certain time, just like with the giraffe. So that means we can use simultaneous equations again. So they haven't told us how to write the model. Before we had h equals mt plus c, and if we wish we can do the same thing here again with r equals mt plus c, but they've given us free range. We could use different variables from m and c if we wished. Substituting in our information, so r is 10.0 where t is 1960 if you wish, and r is 9.58 when t is 2009. Well, I've actually started from when the first world record was set in 1912. So 1960 is 48 years after that, and 2009 is 97 years after that. So on that basis, we can substitute 48 and 97 for our times. And as you see through, okay, we end up with a value of m, which is about -3 over 250, and a value of c, which is about 10.41. So not quite as nice numbers as the giraffe example. So our model is that r equals 10.41 minus 3t over 350. So based upon the fact that I'm starting the time from 1912 and the first world record was set, if we want the world record in 2050, then we need to do 2050, take away 1912 and get 128 for t. Substitute that in there and we get 9.23 seconds. Okay, now notice that this is what we call extrapolation. So in the previous example, we knew the height at 1 year and the height at 4 years, and we were using our model to find the height of 3 years, which is fine because it's between 1 and 4. But here we're using two values in 1960 and 2009 to predict something in 2050. So you have to think about whether that's reliable or not, because if you were to do 1,000 years into the future, then we might start finding people running the 100 meters in negative times, for example, which of course is implausible. Anyway, so for B it's 9.23 seconds. Part C, state the limitation of the model. Okay, well, I've substituted 0 for the world records. Okay, just as an example, again, going back to the idea of it being ridiculous in the future. And if you solve the equation with r as 0, you end up finding that t was in 1215. Of course, that's not the year 1215, it's 1215 years after the first world record was set, implying that in 3127 someone will get a world record of 0 seconds, which of course this does make sense. And of course beyond that, okay, we end up with further times we're going to end up with negative world records as the line increases. Okay, now finally we're using some actual data that the American Carl Lewis set a world record in 1988 of 9.93 seconds. And if we use 1988, it tells us that t is 76. And when we substitute that in, we get 9.76 seconds. Now, we're only talking about data between 10 and 9.51. So that's actually quite a big discrepancy, really, isn't it? Okay, it's 0.17 seconds. Okay, it's only 1.7%. Having said that, as I say, if we're only looking at times between 10 and 9.51, you would presumably expect it to be closer than 0.17 seconds if it was a good model.